Hi guys, this is GKCS. We are talking about a question from the June challenge of Codechef, which is Clone Me. And this question is a little advanced, so there are a few prerequisites that we need to talk about first. Persistent segment trees is one of the things you need to know. If you don't know about it, you can check out the video for that. The other thing actually which comes even sooner is hashing. So hashing is a concept that most people know about, but to know about and to actually know about it in detail is different. So in this question, you need to understand hashing in depth. To actually think about hashing and then apply it to this question requires some understanding of what hashing itself is. Okay, the question itself is quite simple. You have an array given to you and you have q queries of the type A to B and C to D. So these are ranges which are sorted sub-arrays for us. So from A to B, we take that array and we sort it. Okay, this is the sub-array sorted, and C to D goes through the same procedure. We sort all elements in C to D. Now, this is not going to be changing the original array. Okay, this sorting is not in place. It's in an external array. So you have these two sorted arrays now, and it's known that the size over here, the size of this sub-array is equal to the size of this sub-array. Okay, that's also guaranteed. What else do you need? Well, once you have these sorted things, you need to go for every I in this array, so every index over here, and the corresponding index in the second array, you need to check that they differ by at most one element. Okay, so if, let's call this first and second, f and s. So if f of I is not equal to s of I, then we increment a counter, and finally the counter should be less than or equal to 1. If this is the case, you print yes. If it isn't, then you print no. Pretty simple question about range queries, essentially. So, what do you think? So the first thing which occurred to me was using error detecting codes and correction codes. Hamming distance is what we call it. But really, this was just an idea. It's an interesting thing. You can read up about it in the description. There are links over there. But yeah, that's it. It's just an idea. The second thing, which is actually what works, is called hashing. Now, I'll just give you a very small story about how hashing works using some army scenario. So you have an army A, and you also have an army B. And what happens between the two of you is you have a shared secret, a key. Okay, that only the two of you know about. Nobody else knows about this because it's your special army. Now there's a bad guy, C, who can read your messages and who can also stop them and send different messages to B. So you know what's happening. C is going to try to change all messages that A sends to B. Okay, so let's say A does send a message, but A is not dumb. So what he's going to do is he's also going to be adding a hash value to this. So the hash of this message generated using this key is also going to be sent along the message itself. Okay, this is the envelope. Now, C gets this message, kills it on the spot. There's a pigeon or something. And C can read this message. There's no problem over there. C can also replay this message back. That's also fine. But C cannot change the message. That's a guarantee over here with the hash function. Why? Because when C is changing the message, this is no longer the message. It's something called corrupt, let's say. So this is a corrupt message. But C needs to generate a hash for the corrupt message. But how is it going to generate the hash? It does not have the shared key. So it's going to use its own key, which is key 1. Alright, which is going to generate a hash value, hash 1, let's say, and send this to B. Now B can do something pretty smart. B can get the corrupt message and try to generate a hash of it with its own key. That's going to give you a hash value of hash 2. Now if hash 2 is equal to hash 1, then you're in big trouble because B is going to assume that this message is not corrupt. But there's a very small chance of that, so most probably they will not be equal. Hash 2 is not equal to hash 1. B will know that this message has been tampered with and will not follow through on the orders. So one of the examples would be A says attack some random place, C says don't attack that place, attack some other place, and B says okay, I don't believe in the message that I just got. Okay, why are we going through this? Because we need to find out if two arrays which are sorted are the same. So if the hash values are the same, you understand that they are the same, most probably. So what we need to do is find out the hash value of those sorted ranges, and if they are the same, you can say that yes, these two arrays, the entire arrays itself are probably the same. Just like you can say whether the message and the second message that B got is the same or not. Okay, there is a factor of probability here, but the factor of probability is so small that in fact it's more likely that an asteroid will hit us and we'll die compared to us solving this comparative programming problem. So that's a bigger problem, and we'll look into that later. Right. What else? Well, how are we going to generate this hash function? There are a few methods, but in relation with this problem, what you really need is to find the hash of the sorted arrays, and then also to be able to say, okay, at most one of the elements is different. That's what you need. Okay. So how do we find the hash? Well, in the two sorted arrays that we have, they are of the same length, and at most one element can differ. So that means that over here there's going to be an element small a, and an element over here is going to be small b. So this contains less of b and more of a. One less b, one more a. And this contains one more b and one less a. Okay, that's what the two sorted ranges contain. That part is clear. So what we want to do is keep some sort of frequency count, because one less and one more and one less and one more, we are dealing with frequencies over here. So the hash function should be defined using the frequencies of the elements in the sorted arrays. Okay. So if we want a hash function, if we want the hash of this subarray, we are going to be calculating using summation of frequency of all elements I into the frequency of I in that subarray into some base. So b raised to the power I. Okay, for all I. So this is a subarray from 0 to n. That's how we're going to be finding the hash of that subarray. Okay, this function is pretty important. It not only tells us if two arrays are equal, but if you reduce the frequencies correctly, you should also be able to say what is the distance or the difference between the two arrays. Okay, if I reduce the frequency over here and increase it over here and so on and so forth, I should be able to answer whether the distance between the two arrays is at most 1. Alright, now one of the things we need to keep in mind is of course the time complexity. So taking out the hash of every subarray that we're getting in a query is going to be an order n operation, and so the most favorite equation of mine, order qn, comes in, which is exceeding the time limit. So we can't do it this way, not the simple way. What we could do is pre-compute all the hashes of this array. So when you're going through the array, what's going to be happening is you have the hash from 0 to an index I. Let's assume that. So to find out the hash from 0 to I plus 1, what you need is hash of 0 to I plus whatever element occurs, its corresponding base raised to power I. So plus b raised to the power I. And there's one thing I've forgotten here, which is actually we need to take a remainder of this entire thing. Okay, modulo some prime number p. And keep this prime number sufficiently large. I would say 10 raised to the power 9 maybe, plus 7. So this is a prime number, this should work. Now, what else? So every time you're coming across an element, so p of I, let's say a of I is equal to x. So what we need to do is plus b raised to the power x. That's what we're doing, okay? And then we are also modulo that with p. So because 0 is common over here, we skip that part. And what we do is these are prefix hashes. just like prefix sums, the same way we just take the hash values up to a point I. And whenever you need the hash of a subarray from I to j, what you can do is you can take h of j, subtract that with h of I minus 1. And you should get the answer that you're looking for, which is the hash of that subarray. Okay, go through this for some time. There might be some doubts that you have, but they'll get cleared once you do the math. Okay, so what's next? If this hash function for the subarray A to B is the same as the subarray C to D, then we are done. We print out yes. And we thank God because this is the easy part. Okay, after this comes the little complicated part of at most one difference. So when does that happen? Now, like we saw, the first subarray and second subarray are pretty similar. So the first subarray has one element, small a, which has extra frequency. Okay, so that has a little extra frequency, and it has small b, which has a little less frequency than s, the second subarray. These two elements are what we need to find, and if we correspondingly change the frequencies and then the hash values match, then we can say that yes, the two subarrays are differing only by one element. Okay, so to do this, what you can do is you can take the first subarray, which has at most n elements, and you can search for a and b. So for every element, you increment the frequency by 1, and for every corresponding element in the remaining subarray, you decrement the frequency. Actually, you're looking for b now. So you decrement the frequency by 1, and then you check if the hash of this new subarray is the same as hash of C to D. Okay, to calculate the hash of the new subarray is pretty simple. Whenever you are incrementing the frequency, you correspondingly increment b raised to power x. So if x is being incremented, frequency of x, then you just add b raised to power x modulo p. And similarly, when you're decrementing, let's say y, so you will be subtracting minus b raised to power y mod p. Okay, pretty simple stuff to calculate the hash, but unfortunately you're going through the entire array to find a frequency to increment and then to decrement. So this is an order n square operation. Very expensive, and in fact, because you're doing an order n square operation, this is order q n square now. So this kind of complexity is not feasible at all. And I was going through the discussion on Codechef, and one of the really good points made by Sinus070 is that you can use prefix sums and prefix square sums to actually find out the two elements you're looking for. Okay, so prefix sums is a very easy concept. We have discussed this a lot in the previous videos. What we can do with it is find the sum of a subarray, which is A to B or C to D. And similarly, prefix square sums, we are just finding out the sum of all the squares of the elements. Okay, so that can be done for A to B and C to D again. Okay, so what's going to happen here? Well, we are saying that at most one element should be different, which means there's an element, let's call it P and Q now. I know I've been using small a and small b, but P and Q is a better term for this. So P exists a little more in the first array and a little less in the second array, and Q exists a little more in the second array and a little less in the first array. So P and Q are the elements we are looking for. What we should have, if we subtract these two subarrays sums, is P minus Q. Okay? And when we subtract these two sums, we should get P square minus Q square. That tells us that we can get P minus Q and P plus Q, which is this equation, and we already have P minus Q. So we can figure out what P plus Q is, which in turn tells us that we can find out what P plus Q is, and P minus Q is known to us. So we can add these two equations and get 2P, and we can subtract them to get 2Q. And so basically we can find out P and Q. Okay, so we know the two elements that we are searching for in the two subarrays using this technique. That's really nice because we'll need it. Okay, and now we are very close to solving the question. You need a few conditions for the two arrays to be very similar to each other. Okay, the first condition is that the frequency of P in the first subarray should be 1 more than the frequency of P in the second subarray. Similarly, the frequency of Q in the first subarray should be 1 less than the frequency of Q in the second subarray. 2 conditions. And the third condition is that every other frequency has to be the same. So the hash of the first subarray plus b raised to power q, because it has less of that mod prime number, should be equal to the hash of the second subarray plus b raised to power p mod prime number. So if these 3 conditions satisfy, then we are guaranteed that the 2 arrays are very similar and you should print out a yes. Otherwise, print no. If any of these 3 conditions do not satisfy, just print out a no. Otherwise, you can print out a yes. Okay, so we are very close. This is efficient to calculate. We said that we can calculate the hash of a subarray in order 1 time, and these are all constant operations. So that is order 1. The third condition is easy to calculate. How do you calculate the first and the second condition? Right? You need the frequency of an element in a given subarray. So for that comes persistent segment trees. And if you haven't looked into the persistent segment tree tutorial, I strongly recommend that you look at it. mkth num is the question we solved there, and it's very, very similar to how we'll be answering the queries over here. Okay, so let's do that now. So let's just go through this persistent segment tree example and understand how we're going to answer our queries. So this is the array that we are taking, and our initial persistent segment tree has every element set to 0 because it's going to be storing the frequencies of a particular value occurring. So frequency of 3 occurring initially is 0. Okay, and let's take the very first element 1. 1 is now occurring once. Because this segment tree is persistent, you can't change the original tree. That is version 0. We are now going to take the next version, version 1, having 1 frequency for node 1. So that's a lot of ones, but let's take this 1. Okay, everything in red is the new segment tree. In fact, it needs a new parent because 0 is not going to be its parent. So the new parent is 1. This is its left child, therefore we saved on making a node. Here we go higher up the tree to get 1 plus 0 as the new parent, and finally we get a new parent and a new root basically, which is 1 plus 0. So this is version 1 of the tree. Now what? 7. 7 is going to be version 2. Let's use a different color for that. 7 needs to be incremented by 1. So version 2, which is going to be in blue, so this is a new segment tree that we are creating essentially, is going to have 1 as the frequency of 7. Okay. So that creates a new parent which has a left and right child. Similarly over here you'll have a left and right child, 1, and a left and right child here also. So that's this. Should this node point here or should it point to this node? It should point to this node. The reason being that this is the new version, it's going to be using all nodes of the older version to move forward. So it uses the nodes of the previous version basically. Okay, so this is the new tree that we have. Let's just take one final example. Let's just take 2 more examples. So 4 initially has a frequency of 1 once you come to this point. So 4 will have a frequency of 1. Go up the tree, what do you get? Well, you get a new node having frequency 1 because the right child now is still 0. Now you get a new parent which uses this child. Okay, so this frequency is now 2 because there's 1 plus 1, this child. So you see how things are getting a little complicated graphically, but actually implementing persistent segment trees is not so difficult. The code is not really so involved. Okay, now 2. Well, 2 is right here. The parent here of 2 should use 2 as a right child and the left child should still be 1. So this will be value 3. In fact, yeah, 1 plus 1 should have been 2 here, right? So this is 2. Sorry, I don't know, I did change that, but yeah. So that's the new root that we have using these two nodes. So you can see that there are different roots having different values. The first one has 1, the second one, the first one initially, of course, it was 0, then it had 1, then there was a 2, the blue tree, and now this purple tree has 3 as the value. Okay, just one final example so that I run out of colors now is another 4. So 4 now becomes 2, which gives you a parent having value 2 because this is again the other subtree of this node. Now its parent in turn is going to be containing 2 plus 1, which is 3. And finally its parent, which is somewhere over here, let's say, contains 3 plus 1, which is 4. So you see that the frequency at the root, I mean the total number of nodes at the root has become 4 now. So it's incrementing 1 by 1 by 1. But you see that the segment trees are completely divided as per what index you are at. So of course in the code, you can go to any node, any of these nodes in just order one time. And also the maximum number of nodes that you're adding to this segment tree on every update, on every index is log n. Because you're just going up the tree, right? Just going and adding one node per height of the tree. So you will need n of those updates. So that is n log n, a very reasonable time limit requirement. Okay. So how do you answer queries? So one of the things I forgot to mention in the equations that we have is the fourth constraint, that P and Q should have the same index in that sorted range that we are looking at. Okay, because when you're traversing through the sorted range, there should be at most one difference, meaning that they should have the same index in that sorted range. So that's the reason why this persistent segment tree has been created actually, to find the index of an element in the sorted range. Okay. Now, how do we do that? Let's take two examples. Let's say one of the ranges is, what should we take? Let's take 0 to 3. That's one range. And we need to find all elements less than 5. So that's one query. The second query is, in fact, it's not 0 to 3, it's 0 to 2. Okay. And the next query is going to be from 1 to 2. This is slightly more interesting. All elements less than 5 in the range 1 to 2. Okay. So let's just go for the first query, which is from 0 to 2 and all elements less than 5. So 0 to 2, when the second index was updated, that time we went for violet. Yeah, 4, that one got updated. So what needs to happen is that we need the violet color here. This is version 3 actually. But so the index, whatever is the rightmost index, you just need to add that by 1. So we are going for version 3. Version 3 is violet, we go to the root. Now what do we want? All elements less than 5. So we need this range, 0 to 4. All elements less than 5 for violet. So we come to 3, we see that the left node lies entirely within the range, 0 to 5. So this returns 1. Plus, what's on the right range? 2. Does it lie entirely within the range? No. So you go to the left. You're still not sure because this is the range you want and this node answers for both parents. So you go on the left again and you come with 1, which lies entirely within the range. 4 is the index. So 1 is what returns here and we get the answer as 2. Okay. So this is for all elements having the third version. In the third version, all elements less than 5. You need the same thing for the very first version also. The very first version is not the red root, it's the black root. So that gives you 0. If you take the sum over here, you're going to get 0. And so what happens is 2 minus 0 gives you 2. And these are the number of elements less than 5 in the given range. Okay, let's take a slightly tougher example. 1 to 2, all elements less than 5. Similarly, just the exact same way, you go to the violet node and you get an answer of 2 here. But the interesting part is 1 now. So what do you subtract this by? You subtract this by the number of elements less than 5 in the very first version. Okay, so first version means the red node, so that's the red root. All elements less than 5, meaning this range. Well, from 1 you come over here to 1. You see that this entirely falls within range, so 1 plus what? Over here you have 0. You don't really need to go down, but the standard segmented procedure is you're going to go here and then here and then here and keep a 0. And the answer you're going to get is 1 out of the smaller range, the left range. And so 2 minus 1 is going to give you 1, which makes sense because in this range, there's just one element which is less than 5. Alright, now why are we doing this? Because knowing the number of elements less than the element you're looking for will give you the index of that element in the sorted range. Okay, in the sorted range, all the elements are going to cluster together, the smaller ones are going to cluster together. If you know the index, if you know the frequencies of the elements less than a particular element in this sorted range, then you can answer for what is the index of this particular element itself. Okay, basically, from 1 to 2, if 5 existed, its index should have been, because there's one element before it, its index should have been 1. The other element is at index 0. Okay, the other element is 4 over here. So yeah, that's where it should be. But we know that it doesn't exist. 7 will come here, but that's how it is. In fact, you could have searched for 7, all elements less than 7, and you would have got the same thing. Okay, the same answer. So that's how we are going to be finding out what is the index of any P or Q in any sorted range. So what should you search for, P or Q? Go for the smaller element. When you go for the smaller element, you are guaranteed that the two sorted arrays should have P's and Q's after some particular number of elements, let's say X. So it should be the same in both sorted arrays. Okay, so for A to B and C to D, the index of P without loss of generality, let's say P is always a small element, the index of P should be the same in both these queries. So these two should give you the same answer. Alright, and if that is the condition, if that happens and the other conditions that we talked about, finding out the frequency of P or Q is not difficult in this persistent segmentary data structure. So if those 4 conditions occur, then print out the answer as yes, which is a really big deal. Print out yes, or you print out no. If those conditions do not occur, you're guaranteed that they are not similar. So that's it for CloneMe. I've mentioned all the relevant links in the description below. If you have any suggestions or doubts, you can leave them in the comments, and I'll be getting back with dynamic programming with trees as soon as I can. So until next time, see you.